Hi, welcome to this lesson on Euclidean geometry, similarity, and congruency. Let's have a look at similarity in triangles. So just as we've seen similarity in polygons, so polygons, remember, were any kind of shape in the two-dimensional plane with three or more sides. But now we're looking at a very specific type of polygon, the triangle. So there's some nice properties that come out with triangles when we look at similarity and congruency, hence why we spend so much attention towards it. Okay, so we say that two triangles ABC and PQR are similar to each other, denoted by triangle ABC similar to triangle PQR, if and only if one of the following conditions are satisfied. Okay, so if you prove either condition 1 or condition 2, then you have shown that the two triangles are in fact similar to each other. So condition 1 stipulates that all corresponding angles are equal. So if you write it in this order, that means angle A must be equal to angle P, angle B equals angle Q, and angle C equals angle R. So if you show that, then you've shown that the two triangles are similar. However, if you know more information about the side lengths of the triangle and not much information about the angles, then you can show that all corresponding sides are in the same proportion. So again, I do AB over PQ, that must be the same as BC over QR, which must be the same as AC over PR. Okay. So mathematically, this tells us that two triangles in the plane are similar if and only if they are equiangular for all corresponding vertices, or the ratio of the corresponding sides of each triangle are in the same proportion. So we just need to show condition 1 is true or condition 2 is true. If we show condition 1, it automatically implies that condition 2 will also be true. And if you show condition 2 only, it will automatically imply that condition 1 is also true. Okay, so you only need to prove one of the two conditions. So let's have a look at an example. In this diagram, we have that AB is parallel to DE, so that's given information to us. And we've also been proved that triangle ABC is similar to triangle EDC. So first of all, notice that this angle A here is equal to this angle E here because of parallel lines and alternate angles. Similarly, this angle B here must equal angle D here in that triangle, again by the same reasoning. Parallel lines and alternate angles are equal. And then lastly, this angle C here in this triangle is the same as this angle C over here in the bigger triangle. And that's because of vertically opposite angles being equal. So what have we shown? Angle A equals angle E, angle B is equal to angle D, and angle C is equal to angle C. So in that exact same order, we can prove that the two triangles are indeed similar, and the reasoning is angle, angle, angle. Okay, because those three corresponding angles are equal to each other. And because this is true, that means that if I look at the side length AB over ED, that must be in proportion to BC over DC, which is the same as AC over EC. Okay, that's automatically implied by the similarity properties. Okay, and then lastly, if we know now that the length of AB is 4 centimeters, and we're given another additional piece of information that the ratio AC over AE is 5 over 7, they want us to calculate the length of DE. Okay. So because we've just proven that triangle ABC is similar to triangle EDC, which means we can use the proportion of corresponding sides to help us. Okay, so if I let this entire side length here, AE, equal K units, okay, then by this first property that I've been given here, this condition, right, if I multiply both sides by AE, I get AC equals 5/7 AE. But for convenience, I'm just going to call AE K. Okay, so AC, this distance here is 5/7 of the distance K. All right, that means we can work out this remaining piece here by subtracting K from 5/7 K, and we get 2/7 K, because that'll make up the entire distance of AE. That's what we've got here. So now I'm going to use the fact that these triangles are similar, and remember the goal is to find the length of DE. So when I use the similarity property, I need to find one where DE is considered. So I'm going to do DE, right, divided by CE. So within the same triangle, I do DE divided by EC. So look at that way that I took it in that order. So I must do exactly the same thing here for this triangle. So that means I must take AB and divide it by AC. All right, so doing that, I get this equality from similarity. So again, the The reason for that is because the triangles are similar. So if I isolate DE by itself, I multiply both sides by CE. Okay, and the reason we did that is because now we have a representation for CE. We said it was 2/7 K times AB over AC. Now AB was given as 4 centimeters. Okay, so we plug that in. And AC, we worked out, was 5 over 7K. So the reason we did that nicely now is because the K's will divide into each other. Okay, and essentially you have 2/7 divided by 5/7. When you divide by a fraction, you multiply by the reciprocal, 7 over 5. So the K's divide, and we have 2 times 4 times 7 all over 7 times 5. So again, the 7's will divide. So 2 times 4 is 8 divided by 5, and that gives you 1.6 centimeters. So this length here for DE is 1.6 centimeters. All right, so that was using similarity in triangles and using the ratio proportion, right, of the corresponding side lengths to be able to answer this type of question. Awesome. I'll see you in the next one.